whoever can't join now, just download it later. Right, let me share my screen. And let's start with the self-study assignment. So there are 4 questions asked. The focus here was medium voltage cables and partial discharge. Number 1, describe the difference between PILC and XLPE medium voltage cables. The number 1 point here that a lot of folk missed was nobody really defined what a PILC cable and an XLPE cable was. Just went straight into a comparison of the two. So a useful starting point is comparing the 2 cables. We can do that now. Quickly, I went to the CBI Electric African Cables website. And there's an example of a medium voltage PILC cable. When it comes up. Right, so this is a 3-phase cable. You can see your conductor, copper conductor 1. You can see around it, it has paper insulation. Between the copper and paper insulation, it's got carbon loaded paper. Then it's got that for all 3 phases. Then around that, those 3 phases is lead sheathing. Right. So within all of that goes the oil. So it's not just paper, it's paper and oil. Right, so it's a combination of liquid and paper, liquid and solid. Right, and then outside of it, it has some armoring so that if you're trying to dig into it, you find it difficult to break. Environmental elements will find it difficult to get through. On the outside, there's another cover, just PVC sheathing. Right, so that's a PILC cable. An XLPE cable, also 3-phase. You can see it looks a little bit different. I'm not sure why I've selected the aluminium one, but in the middle there, you can see the round conductor. It's a copper or an aluminium conductor. Then that white bit there, that's the XLPE insulation. Right, it's the dielectric. In between the conductor and that insulation, there's a semiconductor screen, as well as on the outside of that. Then there's a screen on the outside. You can see a little copper line there. Right, so that's the single phase cable. And you can see there's 3 of them. And then there's lots of fillers just to hold them in place. So this one is purely solid dielectric. There's no liquid involved here. They offer different advantages and different disadvantages. If you think of a little hole in this insulation, a void, that void is not going to be covered by anything. So that void may end up going into partial discharge. It may end up getting eroded. If you think about this one, if there's a little void in that paper, it's going to be filled with oil. Right, but there's other problems. Oil and paper, if the cable gets too hot, it causes some degradation in the oil, and that can cause other issues. Bubbling can be there can be bubbling in the oil. It can cause what we had cavity breakdown in liquids earlier. So there's other issues that happen in that one. XLPE is definitely the more modern type of cable. And I'll discuss a little bit further just now. Describe a cable joint and cable termination. I think most people were okay with this. A cable, medium voltage cable, it has to have a conductive component. It has to be rated to the correct current. It also has to have an insulation of a certain rating, as well as needs to be protected from the environment. So I was hoping for a bit more of those elements, didn't get as much as I hoped for. A cable joint, so often around Durban, you get faults because we've got a big cable network here, and they dig up the ground and they go there and they join two cables together. They remove the faulted bits, they join two cables together. So that joint has to be better than the cable, has to have better insulation than the cable. So it joins the cable, then you've got to insulate that joint, then you've got to protect that joint. So it's very important to get that joint correct. Cable termination. So this is where the cable can come up and join a transformer or a piece of switchgear, etc. It's very important that that's also got the correct insulation. Remember, you're taking high voltage, you can't just put it out. You actually need a specific type of termination to control the electric field, to protect it from the elements, to protect the cable internally, to make sure that the oil is not going to leak. So there's a lot more to it than you actually think. What I didn't like to see were the mentions of telecommunications and signals. This is not telecoms engineering. There's no communication happening in these cables. It's not signaling. This is for power distribution. So it's transmitting power. Describe the failure in a medium voltage cable. There's a number of things that you could have looked at. I think most people were okay here, or at least I've started giving highish marks here. So the cable joint, and the cable termination can all fail in different ways. The cable, it could be a long-term thing where there's a slight defect, partial discharge starts occurring, and it continues to occur until complete breakdown happens. Cable joint, you could have an incorrect installation. You could have a bit that wasn't clamped properly or crimped properly, and that could cause a hot spot, causing the insulation to degrade a little bit, and then the electrical side, partial discharge starts occurring until it fails completely. So there's a lot that could have been said there. Describe what I didn't like for question 3 is where folk referred to low voltage cable faults, such as overheating of wall sockets. So these are the wall sockets that you get in your buildings. That's not medium voltage, that's low voltage. Where people refer to using a multi-plug adapter and overloading it, and that's what caused a failure. So I didn't like that at all. There's nothing to do with medium voltage cable. Right, describe 3 methods for measuring partial discharge. So yeah, the first method we'll discuss, the laboratory-based method we'll discuss just now in the course notes. It's where you've got a coupling capacitor and you've set up your system to read the partial discharge. Other methods would have been putting an HV2 around an aspect of the conductor. So normally you can't get an HV2 to certain places, but certainly if you've got a lead coming out somewhere, such as in a cable termination, you can connect an HV2 there. There are methods to connect close to the termination where you could put a coupling capacitor as well. You could also have some sort of RF antenna to see if you could locate a partial discharge. What was important here is that it must be focused on the cable. I didn't like it when folk put a UHF antenna into a transformer and were indicating that was a method to measure partial discharge in a cable. That doesn't sit nicely. All right, you must state in your answer what indicates good cable insulation and poor cable insulation. So I got answers such as the leakage current is higher in poor cable insulation, or the tan delta is higher. The assignment was about partial discharge. So those things may be true, but what I really wanted was partial discharge. So it could have been the frequency of the partial discharge, or sorry, the repetition rate of the partial discharge. It could have been the values of the partial discharge. You could have related that to whether it was good insulation or poor cable insulation. Right, that was the self-study assignment. Okay, I'm going to close that. And we're going to go through the course notes. And then I'm going to go through some drawings to support that. All right, partial discharge. It's a localized electrical discharge that only partially bridges insulation between conductors. So that's key. It's not a full discharge. It's not a disruptive discharge. So it's a very small discharge in only part of the insulation. So they are a result of local electrical stress. So solid and liquid insulating dielectrics, they may contain voids or cavities. It could be at the boundary of the dielectric and the electrodes. It could be in the material itself. So what's critically important is that often the cavities are filled with the material with lower dielectric strength than the dielectric. So we found in HV1 that air, for example, had a much lower breakdown strength than oil or your solid dielectric. So if we just take the example here of what's drawn, if that little white spot there is a cavity filled with air, that breakdown strength is going to be much, much lower than the solid strength. So if you put an electric field across there with a high enough value, it's going to break down in that cavity before it even breaks down in the dielectric. So that little breakdown, it's got energy, and that's going to cause a little bit of degradation on the surface, on the material. And that's going to continuously happen. Right. The partial discharge initiation voltage was covered in HV1. The equivalent circuit of a cavity, if we just have a look up here, you've got a permittivity. So you've got a capacitance between the two electrodes. Then you've got a capacitance of the cavity itself and a capacitance CB of the remaining material. So that's how to represent the insulation and the cavity. What happens when that breaks down? So when there's a capacitance, when there's no breakdown, as soon as it breaks down, there's a short and a little current flows in some sort of resistive type of manner. So you've all seen this before, or I hope you have, where you've got a charged capacitor, and if you touch the two terminals, you see a little spark, and then it discharges. So same thing here. The capacitor it discharges through some sort of equivalent resistance. So what that's saying is that it's charged up with Q and it discharges. So if you look at equivalent circuit for measuring partial discharge, you can see on your right is a piece of insulation with a little cavity in the middle. We've got a voltage source, an impedance, and what we call a coupling capacitor. As soon as it's a little discharge there, there's going to be a current in our circuit. Right. So that discharge Q is going to give us a current in the circuit. That's cool. That means we don't have to go and see what's actually going in there. It's internal to that. We can measure it externally with the circuit. That little current or that little discharge, it's going to cause a little voltage drop in the circuit. And that's given by equation 4. And Q, if you can't measure the current directly, will be given by that, the capacitance, the known capacitance, and the voltage drop. Right. So normally the charge, it's difficult to quantify the charge because your circuit often consists of many different capacitances. You could be measuring a cable of 10 meters one week and a cable of 100 meters the next. So that all alters how your measurement system measures. So normally we have to calibrate it. Yeah, we have to calibrate it with a known way to do it. So we calibrate it with a known source, and that gives us a reasonable guesstimate of what the charge should be. Right, so I just want to point out one more thing here. The apparent charge is measured in picocoulombs. So that's very, very, very small. We're talking of amps of picoamps and nanoamps. So it's a very, very small charge, very small current pulse. That's why this equipment is so expensive. According to the IEC, there are 2 circuits to measure this. The first is your CT, which is your, if you look here, your CT is your your device under test. So that's your cable, for example, and you connect that to a coupling capacitor, and your coupling capacitor is attached to a coupling device. We'll talk about that coupling device a little bit later. But if you get a current in that circuit, you can measure it with your coupling device. And that can go to your measuring instrument. Simplest measuring instrument, think of an oscilloscope. And your second circuit is where you connect your device under test directly above your measurement, your coupling device, your measurement impedance. So again, think of the current circling in that setup. There are a couple of important aspects to the setup. You can read through some of them yourself, but I want to point out that Z, that impedance there, that impedance has to be completely noise-free, and it needs to be of high enough value that it blocks any of those discharges. So those discharges, you want to stay within your measurement circuit. You don't want them to flow through to the source. You want them to flow around your measurement circuit. All right, I'm going to swap over to the iPad now, and just cover some stuff that we've spoken about already. Right, so we've got our device under test, that's in the red. We're applying a voltage across it. You can see a little yellow spark in the middle, that's the discharge, and a current flows in our circuit. Just to give you an idea of what sort of current we're looking at. Sorry, that's not very clear. We're looking at picoamps and nanoseconds. So it's a very, very small discharge. If we put this into a circuit, put this into a circuit, you can see that if there's a coupling capacitor, the charge comes from the capacitor and we can measure it accordingly. Guys, I'm struggling a bit here. I've got a bit of a cold, so I'm struggling to speak. What I'm going to suggest is that I update the class on Moodle about the main assignment, and then I just repeat some of the stuff on Thursday. Is that okay with everybody? Okay, cool. Thanks for attending. Sorry about this. I just can't speak much more.